In this video, we are going to do an example where we find the circulation of this vector field if I go counterclockwise around a triangle with these vertices. And recall that circulation means the flow of the vector field around a closed curve. So let's start by drawing a picture. So I can draw my axes. I can draw my y-axis and my x-axis. And then I'll draw the triangle. So it's got a vertices at 0, 0, and at 0, 2. And at 3, 0. And if I connect those to make my triangle, we get something like this. So we get our triangle, these three sides. I'm going counterclockwise around it, so I'll draw these direction arrows. Okay. To get a feel for what the vector field looks like, let's draw a few vector field arrows. So if I take the point 0, 2, and I plug that in, because y equals 2, this becomes just I hat. So that is going to be a vector pointing straight to the right with length 1. In fact, at any point on the line y equals 2, if I plug that in, I'll get I hat. So even over here, I'll get a vector pointing to the right of length 1. If instead I take a y value that's smaller, like y equals 1, and I plug that in, this becomes 1/2 I hat. So I'll get a vector now of length 1/2, still pointing straight to the right. And then I'll draw a few of those at this y equals 1 level. So again, these vectors just point straight to the right. They have this length of 1/2 now. Okay, and if I go even smaller, then the length shrinks even more. So over here, I'll get an even smaller length, and I'll draw a few example such arrows. Okay, and finally, if I reach the level where y equals 0, if I plug those into this, I just get the 0 vector. I get the 0 vector. So these would just be, points. Okay. So, I have a sense of what this vector field looks like. So remember that what flow means is, as I'm traveling along my curve, it's sort of the degree to which the curve, that direction, aligns with the direction of the vector field arrows. So on this portion of the curve, I'm traveling in a direction that's generally against the direction of the vector field arrows. It's against the grain. So I'd expect the flow on that portion to be negative. The term circulation just means I'm calculating flow, but around a closed curve. So a curve that starts and ends at the same spot. All right, so let's remember that our formula for circulation, for flow, is I do a line integral over my curve, my vector field, dot dr. Okay, and because I have a triangle, there's these three sides, which I'll label. Let's call the one on the left C1 and the bottom one C2 and the one on the right C3. I need to split this up into three pieces. So I'll do the line integral over C1 f dot dr plus the line integral over C2 of f dot dr plus the line integral over C3 of f dot dr. Okay, so we have these three line integrals to do. So let's talk about a couple of them. There's a couple of them that I can figure out very quickly just using the geometry of the picture. And then there's one I will have to work out in more detail. And for that one, I'll give you a chance to pause the video and to try it. So what about for this first one? So that's over this path here, this vertical path on the left. So I noticed that on this path on the left, the direction of my curve is totally perpendicular to the direction of the vector field arrows. So I'd expect this to be no flow. I can verify that mathematically by thinking about my formula for a line integral of a vector field. It involves having to do our vector field and you dot it with the velocity vector. So you'll convert it to a regular integral that goes from a to b, f dotted with the velocity vector dt. And remember that the velocity vector is tangent to the curve. So if I were to take some point on the curve, that velocity vector is going to be tangent. Okay, and if I take the dot product of this velocity vector and my vector field arrows, which are perpendicular to it, well, that dot product will become 0 because they're perpendicular. So this first line integral should just be 0 because our vector field arrows are perpendicular. I'll write this perpendicular symbol to the velocity vector that's directly tangent to the curve. Okay, what about for the second integral? So for the second one, my vector field on C2 on the bottom, well, all the vectors are just the 0 vector, right? Because y equals 0. So because my vector field just becomes 0 on that curve, this integral is going to be 0. So this is 0. Let me separate these. Because our vector field equals the 0 vector on that line y equals 0. Okay, so 2 of these I get sort of for free based on the picture. The third one I actually have to work out. So at this point, I want to have you pause the video. Pause the video for at least 4 minutes to try it from here. So pause it in 3, 2, 1. Pause it and try it. Okay, so hopefully you did that. Let's talk about it now. So I'm going to highlight this third integral. And let's work out what that is. So for that integral over C3 f dot dr, what I need to do first is I got to parameterize the curve. So in fact, let me give myself a bit more room here. I got to parameterize the curve. So I have this line segment for which I need to know the initial point. The initial point on that line segment is -3, 0. And I need to know a direction vector. So direction vector. So I take the ending point minus the initial point and turn that into a vector. So I'll get -3, 2. And then for my parameterization along that segment, I'll call that r of t. You take the initial point, but you turn it into a vector. So 3, 0. And then you add to that. We add to that t times our direction vector, -3, 2. And if we combine these, this becomes 3 minus 3t, 2t. All right, and we've seen that when we do it this way, our domain for t is going to be between 0 and 1 for a line segment. Okay, so I got r of t here. I'm going to need to get this velocity vector, so let's get that. So my velocity vector, that's going to be the derivative of r of t. So the derivative of the x component, I'll get -3. The derivative of the y component, I'll get 2. Okay, so from there, I'm ready to start to evaluate my integral. So this will convert to a regular integral, where t goes from 0 to 1. And then I take my vector field, but I'm going to be plugging in my parameterization for r of t into that. So I notice that there's a y here, so I got to plug in what y equals from the parameterization, which is 2t into that. So that'll give me the vector where that x component, I'll get 1/2 times, and then I'm plugging in 2t for the y. So that's the part with I hat. There's nothing with j hat, which means that component is 0. So I get this. I need to dot that with my velocity vector, -3, 2, and then dt. Okay, nice. So I'm ready to take the dot product. I got the integral from 0 to 1. Multiplying this out, I get t times -3. So -3t, and then plus 0 dt. From there, I can do the antiderivative, which gives me -3/2 t squared. And then I evaluate this at 0 and 1. And doing that, this becomes -3/2. Okay, so that is this third integral. So the third integral is -3/2. The other two were both just 0. So summing these, we end up getting, we get 0 for the first one, plus 0 for the second one, and then plus -3/2 for the third. So overall, I get -3/2. And there we have it. That is our circulation. So in the next section, we are going to introduce another version of Green's theorem specifically to deal with circulation. It'll give us another way to do this, where instead of having to split this up into 3 integrals over each of the sides individually, we can instead do it over this 2-dimensional region inside, and we'll use a double integral.